All right, guys, it's Thursday, so we're going to take some time in the beginning of class today to review some concepts that we learned about on Monday and Tuesday and reviewed on Wednesday this week. You will be able to use this information to help you create a notes sheet for today's quiz, so make sure you are paying attention and writing information down as we go. All right, let's get started. So we started everything off by watching a brain pop video on Monday, and that video was related to humidity. And one of the activities that you did was you had to match some vocabulary words together. So we're going to quickly review those vocabulary words right now so you have a very firm understanding of what they mean before you take your quiz today. All right, so let's start off first. Our first word was humidity. And humidity, we know, is the amount of water vapor that is located in the air. So that makes humidity E. Very closely related is relative humidity. Relative humidity, remember, is a percent. So relative humidity is the amount of water vapor held by air compared with how much it can hold. So that's C, and remember, we're getting that number as a percent. The next is dew point. All right, dew point is when air is fully saturated. So think of a sponge that is completely full of water. It's fully saturated. So this water vapor, which is in the air, that water vapor condenses into actual water. So the dew point is when water will go from a gas to a liquid, and this is based on temperature. So that's going to happen when it cools off, and that is dew point is D. Evaporation, we know this simply as when water changes from a liquid to a gas. So think of having a pot of water on the stove if you're going to make some noodles or something, and you see that steam rising above it. That is an example of evaporation. That liquid is turning into water vapor, or the gas that's floating all around us. So that makes evaporation A. And last but not least, condensation, the opposite of evaporation. So condensation is when water changes from a gas to a liquid. Condensation happens when things cool off. So condensation and dew point are related because dew point will be reached when temperature cools off, and that is when gas will turn to a liquid. So that makes condensation letter B. One of the key points that we know about humidity is shown on the graph to the left here. And what we see on the graph to the left is on the x-axis we have temperature, and on the y-axis we have water vapor capacity. And remember, capacity is just the big word for how much it can hold. So what we see happening is that as temperature begins to increase, so go this way, as temperature begins to increase, so does the ability of air to hold water. So this goes back to that one of those main points, which is warm air. So warm air can hold more moisture. And part of the reason for that is that in warm air, you have those air molecules spreading out a lot more. So instead of them being really close together and then trying to fit some water molecules in there, you have air molecules that are more spread apart, which can allow more moisture to be held in that same amount of air, just based on temperature change. Let's try to hit this concept of temperature and water vapor one more time. I want to make sure that we've got it super, super solid. So I've got two shapes here. And if you're in Hamlin, you remember this. I think in Howard, we might have glossed over this piece. So take a watch and write down some of this information so you can remember how temperature and water vapor are related. Okay, so this larger box here is going to represent a area of warm air, and this smaller box is going to represent an area of cooler air or cool air. Okay, so what I want us to think of as each one of these is just like a container, okay? And I'm going to take in each one of these containers, I'm going to add 4 cups of water, all right? So I'm filling them up with moisture. So I'm going to add 4 cups of water to this larger container and 4 cups to this smaller container. And what happens when I add the 4 cups to the warmer container is that it fills it up to about right here. So I've kind of got this area filled of the container with water. Now just imagine for a moment if I take that same amount of water that's in the warm container and I pour that into the cool container. Same amount of water. Okay, so let's take this 4 cups and let's pour it into the cool container. Not only am I going to fill the container, but I'm also going to spill that liquid on the outsides here. So I'm going to make a pretty big mess and probably not make somebody happy here. But the point is, if the air is warm, it has the ability to hold more moisture than cold air does, which means the cooler air is going to reach 100% humidity much faster than warmer air will because it has less space to hold that moisture. We spent a lot of time on Tuesday looking at graphs like this. And this one is really the money maker. It says it all right here. It links temperature, humidity, dew point, precipitation, saturation. All of those things show up in this one graph. So we're going to break it down into like 3 major points. Okay? The first point that we want to make while looking at this graph, and I'm going to write it first and then I'm going to show you on the graph, is that temperature and humidity are opposites. And what I mean by that, and I'm going to show you on the graph, what I mean by temperature and humidity are opposites is that when temperature, which is the orange line, not the dotted one, but the solid one, when temperature, okay, is low, let's choose 6 a.m. right here, okay? When temperature is low, if they're opposites, then that means humidity is high. And it is. Humidity is this thicker line that's up top here. So at 6 a.m., it's at like 100% humidity. And remember, the reason that they are linked is because cold air cannot hold that much moisture. So that means that cold air is going to reach 100% humidity way faster than warmer air will. So that is the first thing that we can tell from this graph. Temperature and humidity are opposites. The second is that when the dew point and temperature are close, so that means that when the lines are starting to trend towards each other, kind of meeting each other like this, when they are close, that is going to equal, sorry, those two things look like equal signs, equal high humidity. And again, we should see this on the graph. I'm going to switch over to blue color so you can see what I mean for this point. Okay, so dew point and temperature, when they start getting closer, so temperature, remember, is the orange line, and dew point is the orange dotted line. Okay, so temperature is trending down, dew point is fairly steady, and when those two meet, when they are so close that they meet or even temperature dips below, like our problem was today, you can see that at 6 a.m., when they're really close, again, that's when we have our highest humidity at a 100%. the last point I want to make on this graph has to do with humidity and temperature again. And the simple point is that humidity and temperature are going to change based on the heating of the air from the sun. So remember, the sun equals everything. Okay, without the sun, we don't have weather. Without the sun, we don't have climate. We don't have all of these changes. You could go as far as saying that without the sun, we don't even have life on Earth. So the sun changes temps, which then changes the relative humidity. And there are 3 points, and I'm going to do this one in red on the graph here. You can see if the sun is heating up the Earth, heating up the air temperatures at around 6 a.m., and we should probably have the coldest temperatures, and we do, because remember that thick orange line is the temperature. And as the day goes by and the air is heated up, you'll see the temperature rise. And because we know that humidity and temperature are opposites, we should see humidity at its lowest. And then again, you'll see the temperature go back down as we start getting away from our direct sunlight during the daytime. Of course, that's midnight. So that cyclical change is also going to affect humidity. I'm going to finish this review by pulling a couple of questions out of Tuesday's work packet. So these were at the end of the packet, and we'll just go over the answers right now because I think they're really good representations of connecting everything that we've talked about so far. Humidity, moisture holding, water vapor, saturation, capacity, all that stuff. If you hear any noise in the background, that's my really big dog drinking water. She likes to drink a lot of it. So let's take a look at this. The question says, which graph represents the relationship between the moisture holding capacity of the air and the temperature of the air? So what I'm doing is I'm looking at all the graphs right now, and I'm noticing that I've got an X and a Y axis labeled the same for all of them. So let's just take a look at the very first one here. So atmospheric temperature is on my x-axis and capacity to hold moisture is on my y. So I know that as I am moving further away from 0, which is pretty much right there, the temperature is going up over here, which means that as I'm going away from 0 for the moisture holding, this means that I should be able to hold more moisture as I'm going up. Okay, so this first graph is telling me that as temperature goes up, I can hold less moisture. The second graph is telling me that as temperature goes up, I can hold more moisture. Third graph, and I just realized right now that this should be, let's make that 2, and this one's 3, okay? And the third graph right here shows that as temperature goes up, moisture stays exactly the same. So it doesn't go up, it doesn't go down, it just stays exactly the same. And then the fourth graph shows that as temperature goes up and then stops, so let's say it stops at like 40 degrees, which we know is not realistic because temperatures are always changing. So it's saying that if it were to stop at a specific degree, the temperature, the moisture holding would go up. And we know that that is not realistic. So when I think back to the relationship, I know that when air heats up, it can hold more. And more moisture is what we mean. So its capacity goes up. So as air heats up, the capacity goes up. Okay? So what I should see is I should see this trend right here. As temperatures go up, my moisture capacity also goes up as well. So that would make number 2 the correct graph that you see right there. All right, last review question before we get closer to this quiz here. On the graph below, place a star next to the spot where precipitation is most likely and a triangle where precipitation is least likely. In order for me to get this question correct, I need to remember what precipitation really means. Okay, so in order to have precipitation, I need one of two things to happen. Okay, so the first thing I need is temp and dew point, and I'm just going to use dP here. Temp and dew point close together. Okay, so if I look at my graph right now, I can see that the two lines that I have are actually air temperature and dew point. So I already know that I've got a clue to be able to answer part of the precipitation question here. The second variable that can equal precipitation is a high relative humidity. And if I look at my graph, I can see that the two things that I have are air temperature and dew point. I actually don't have a relative humidity line. So this might not be a valuable one for me to consider when I'm trying to answer this question. So remember, it's two parts. Place a star next to the spot where precipitation is most likely, and I'm going to start there first. Okay? I know precipitation is going to happen when temperature, the air temperature, and the dew point temperature, essentially the same things, are close. So when I look at my graph, I can see that at about 6 a.m., I have air temperature and dew point temperature meeting at pretty much the exact same spot there. I know that that is a clue that precipitation can happen, so that is where my star belongs. The next mark I need to make is a triangle where precipitation is least likely. The opposite side of this is I know that precipitation will not happen when these two are far away. Okay, so if they're far from each other, precipitation is most likely not going to happen. In fact, it can't because the relative humidity is so low. So all I want to do is look at my trend lines here, and I want to find the spot where they are furthest away from each other. And that looks like around 3 p.m. So 3 p.m. is where I'm going to go ahead and put my triangle and say that that is least likely there, and that it is most likely at 6 a.m. And that also makes sense too, based on how the air temperatures change from the sun's heating. Colder at 6 a.m., warmer at 3 p.m., so that's going to change my relative humidities. All right, there you go. Make sure that you got the final notes written down, and we're going to get started on this quiz momentarily. Good luck.